Hello, we have been tasked with generating a plan to extract ore from the main zone of the Genoa deposit through the use of technical analysis. The Genoa site has a copper deposit located in North America. The copper deposit is contained within sedimentary rock and implies the source was developed after the rock formation occurred. In sedimentary hosted deposits, the ore forms through a vein in the deposit as a result of previously fractured or breaking rock near a fault zone. The copper deposit is in a flat forest environment with no significant mountain ranges or hills to impede production. Similarly, minor amounts of silver in the deposit have been found, but are assumed economically unjustifiable. The copper deposit ranges between depths below surface of 60 to 280 meters. Ore found in the mineralization zone is surrounded by sequences of laminated sandstone, siltstone, and shales. The thickness of the mineralization is between 0 meters to 6.1 meters. The main zone has a shallow dip between 8 to 12 degrees and strike of 285 degrees. The shallow deposit infers uniformity in joint spacing and stress conditions in the mineralized zone and consistency in material grade. Characteristics of the copper deposit Genoa infer a classic room pillar mining method should be implemented. Room pillar methods are highly cost effective and essential for ore bodies with a dip angle between 0 to 15 degrees. Although sandstone and siltstone are potentially unfavorable pillar material, a naturally supported room pillar method can provide sufficient support due to depth and negligible vertical stress of the mineralization. When considering other potential methods as shown in the table, an increase in pillar size will still be more cost-effective than using fill methods to reduce the stress experienced by shales and siltstone material. Other projects were also shown in the table. A regular ruin pillar is more selective as pillars are put in lower grade areas. However, the grade in the main zone is consistent and changing pillar locations will not result in a greater recovery.
The metal price of copper is of extreme importance in determining the economic feasibility of the Genoa deposit, and in particular, the cutoff grade. Genoa, being a massive copper deposit, will benefit from a long mine life, which reduces the impact of short periods of reduced price once production is running. Copper is mainly used for electrical wire, approximately 60% of the consumption. The rest goes to plumbing, industrial machinery, and alloys. Despite this ensuring the long-term demand, the short-term demand is cyclical and subject to change from many factors. The current copper price is $5,762 per ton. This is a low point, and the price is forecasted to rise to $6,050 per ton in 2020. Using a 3-year trailing average, we can determine that the average price of copper has been $6,284 US per ton. This number is significantly larger than the forecast of $6,050 per ton, but should account for the long-term increase in demand, which will cause the price to rise throughout the life of the mine. The cutoff grade was calculated using the mining, overhead, and processing costs. Because the product is sold as a concentrate, the sales cost of marketing and refining had to be changed to incorporate this fact. The break-even cutoff grade for the Genoa deposit is 0.72%, and the internal cutoff grade without the mining cost is 0.3%. At these values, there's a tonnage of 46 million tons of ore and an average grade of 1.5%. The grade tonnage graph is shown below. As you can see, as the tonnage rises, the grade drops, and vice versa. Considering the shallow depth, low dip, and high tonnage rate of the Genoa deposit, an inclined ramp belt conveyor is the best option for transport of the ore from depth to the surface. As a large conveyor system has a capacity of 3,629 tons per day, 2 will be necessary to handle the maximum milling capacity of 6,000 tons per day. The ramp will have a total length of 326 meters, assuming it is driven through the minimum overburden of 60 meters. The ore will be initially handled by load haul dump machines, where it will be extracted from the stope and brought to the main ramp access point. The conveyor belts have a capital cost of $29 million, assuming the conveyors each cover half the distance of the strike and total distance of the ramp. Accounting for the 5 meters required for the chosen equipment discussed later on, and another 5 meters for mine services such as water, electricity, and the conveyors, brings the total ramp width to 10 meters. Using an empirical formula, the Genoa deposit was estimated to require 600 megawatt hours per day for the entire operation. However, only 40% of this goes to the underground operations, as processing is very energy intensive. This will be provided at depth by ramp wiring with booster and splitter stations where required, and it will be sourced from a municipality if available, or on-site generation such as a power plant or small diesel generators, depending on what is required. Ventilation will be circulated by fans pushing fresh air down the main access ramp and into the mine to dilute harmful gases from exhaust. Another empirical formula was used to estimate the requirement of the mine at 240 meters cubed per second of fresh air. When combined with the ramp area, this means an air velocity of 5.3 meters per second. The ventilation system will be supplemented with boosters throughout the ramp and provided throughout the mine via an auxiliary ventilation system. Pressurized air is required in all mines as it is used to run many auxiliary and support equipment. It must be pressurized to 7 bar, and it will be pressurized by a surface plant. Using another empirical formula, the plant capacity was estimated to be required at 322.4 meters cubed per minute. However, this is becoming less important as mining technology phases out pressurized air in favor of battery-powered tools. The service water requirements of the mine was estimated to be 750,000 liters per day via an empirical formula. The water will be pressurized in a secondary sump storage unit after dewatering and made accessible to working areas and key points in the mine via auxiliary piping. To ensure the safety of the operation in case of an unprecedented storm, we will account for emergency water storage that would be needed by using 15% of the yearly precipitation arriving in one day. This means you would need 1.21 megaliters of storage, and it will be linked to underground via ramp piping. Controlling the water balance by lowering the water table will be a necessary step to extract ore and construct the mine, but dewatering will have to continue throughout the entire life of the mine. This will require much pumping. To determine how much pumping would be required, a water table was set up that calculated both inflows and outflows, inflows such as groundwater, diesel exhaust, and outflows such as surface water or moisture, and the required pumping. This generated a value of 2.7 million liters of pumping required per day. To get the water all the way out of the mine, an extra booster pump midway up the ramp may be necessary. Other mine layout services are also necessary, such as washrooms and refuse stations. These will be put in accessible places for the workers. There will also be a workshop on the surface near the portal, as the depth of the mine is not deep enough to warrant an underground workshop. The workshop will have enough capacity for 2 load-haul dump vehicles and room for extra small maintenance. Stench gas will also be provided through the mine via the ventilation system.
The modified Q-tiling quality index Q prime is developed to determine the strength, stability, quality of a rock mass. Q prime is based on the rock intactness, jointing conditions, and degree of fracturing. Given on the right is the Q prime equation. RQD is the rock quality designation index, which is given as 88% in the parameters. JN is the joint set number. For deposits with 2 joint sets, the joint set number is equal to 4. The joint roughness number, JR, is equal to 2, as the deposit roughness is defined as smooth and undulating. JA, the joint alteration number, also has a value of 2, as the deposit bears slightly altered joint walls with sandy particles. The stability graph method is used to assess stope stability and design dimensions. The stability number N prime uses 3 adjustment factors: A, the rock stress factor, B, the joint orientation factor, and C, the gravity adjustment factor, along with Q prime to develop the stability equation. The figure on your right identifies the relationship between the calculated stability number and the hydraulic radius. Naturally supported mining methods, such as room and pillar, infer a mining operation that is stable with support. The figure suggests when using room and pillar method and a stability number of 14.08, the mine is at a hydraulic radius equal to 10 meters. The hydraulic radius can be used to calculate the length and width of the surface being analyzed, where each room is assumed to be square. Using the hydraulic radius calculation, the length of the room was calculated to be 40 meters. The tributary load method assumes a large mining area and vertical pillars with equal dimensions. The method infers a regular square pillar arrangement and traditional room and pillar design method. The pillar arrangement designates the strength and stress of a rock, while the pillar and opening width were assumed as half the hydraulic radius. Calculating both pillar strength and pillar stress resulted in a factor of safety of 1.46. Based on the pillar width and openings, the recovery can be found as 75%. Given the factor of safety, the barrier pillars will be instituted to ensure mine safety and stability over time. The maximum thickness of the ore body at 6.1 meters indicates that a single pass stoping sequence should be used for extraction. A ramp built going through the center of the mineralization zone will be accompanied by a conveyor where it will bring the material from the working level to surface. A longitudinal drifting and slashing sequence will be used to develop the 40 meter by 40 meter room. Mining will proceed by first developing the pillar in the working area, drilling holes in the rock face in the row using a jumbo drill. Once the holes have been loaded and blasted, the LHD will pick up the fragmented ore and bring it to the conveyor.
As economic factors push equipment to be as large as the constraints of the operation will allow, and the Genoa operation will be operating with a large tonnage and does not need extreme selectivity, the large capacity CAT R3000H will be the LHD used in the mine. This loader has a recommended clearance width of 5 meters, which is within the constraints of the room design, and offers the maximum capacity at the size. To calculate how many are necessary to provide a rate of 6,000 tons per day to the conveyor systems, cycle time will have to be predicted. The cycle time is predicted by encompassing the loaded traveling time, unloaded traveling time, and the hydraulic cycle time to load and unload. This gave a cycle time of 15.84 minutes on average, which is equal to 58 trips a day. With 58 trips a day and 20 tons per trip, 6 CAT R3000 loaders are necessary to provide a rate of 6,000 tons. To account for maintenance and machine failure, an extra loader will be purchased. Financial costs for CAT products are unavailable, but the best estimates place the cost of an LHD at approximately $1 million, bringing the capital cost to $7 million. Drill jumbos will be required in the Genoa operation for drilling of blast boreholes in the working face. The selection was based on the smallest area of the working face and the largest area. A double boom drill jumbo is preferred for its increased working rate and can work on openings as small as 8 meters and is therefore within the limits. It can extend slightly over 100 meters. Because the large working face is 244 meters, 2 double boom drill jumbos and a single boom drill jumbo will be used. The single boom jumbo will be especially valuable when varying thickness and working face becomes very small. When it is not required, the small drill jumbo can be used for rock bolting purposes. Support equipment will also be required for the operation. The main support equipment required was considered to be rock bolters, which will lead the drill jumbos, and therefore one was purchased for each double boom drill jumbo. Many pneumatic machines for small tasks such as bolting auxiliary ventilation to the rock will also be required. The requirements are shown in the table to the right and come out with a final capital cost of $12 million.
Based on previous calculations in the grade tonnage section, the total extracted tonnage is 46 million tons. Assuming production starts in year 1 at 360 days per year, and the daily tonnage remains constant throughout mine production, the life of mine is calculated to be 22 years. Yearly costs will be based on mining costs, G&A costs, and processing costs. If the schedule were to be optimized to yield the greatest NPV, this can be done using online programs and linear modeling. Based on the information presented, mining operations for the main zone in the Genoa deposit are feasible. The room pillar method is acceptable under given conditions, with a room of 40 meters by 40 meters and pillars spaced 5 meters apart, such that 12 pillars are required. Room development will be stable given proper supports and a higher QD, and the mine is assumed profitable based on metal prices and associated costs. Thank you for listening to our presentation.